figure out a strategy in which all four of them safely reach the other end of the river. This is a classic logical puzzle. I think we have done it in our childhood. So if you give this puzzle to older models like GPT or even GPT-4, they usually fail at this kind of problems. They fail at reasoning the intermediate steps. But if you try it nowadays with reasoning LLMs, they'll give you the entire thought trail and they'll also solve this correctly. We'll see in a short while. So, what happened to this? Yeah, this is another mathematical problem which requires the model to reason out step by step and then figure out the correct answer. So how do we build this AI reasoning? Now, there are two classical ways. One is to use logic and rules and somehow hard code the rules into the model, which is called logic-based or symbolic AI. Or you can use neural networks which automatically detect patterns and then use those patterns as rules to figure out reasoning and to implement reasoning on a problem. So, essential property of these reasoning kind of tasks is that they have a deterministic answer. They have a verifiable answer. This is exactly this property which has been used by the inventors of DeepSeek and other reasoning models to train these generators to train the basic foundational models to be reasoning models. We'll see this ahead in the talk today. What are the common reasoning models? We have Cloud 3.7 Sonnet, we have OpenAI's O1 and O3, then we have DeepSeek R1, and there are many more coming up every day. So such reinforcement learning based LLMs are actually your problem solvers, which can be used for your mathematical or logic or research oriented tasks. Here is how a standard LLM is trained. This is the entire training life cycle of your GPT-4, let us say. So it undergoes pre-training where it is shown tons of data, trillions of tokens, trillions of bytes of data, and it learns the language model, it learns the probability of each correct sentence, and then it becomes a perfectly good next token generator or next sentence generator or next word predictor. But that's not all. That makes it a good speaker, but it doesn't increase its reasoning capabilities. For building those reasoning capabilities and for aligning these models better with human preferences, we perform a second layer of training, which is called supervised fine-tuning. What exactly happens in supervised fine-tuning is that humans generate a large number of prompts, or we can use another model to generate a large number of prompts, and we use another model to generate responses for those prompts, and we fine tune these models. We perform another bit of training of these models on this supervised data set. This is called supervised fine tuning. And it has been observed then with SFT, a lot of models perform a lot better even with natural language generation tasks and reasoning tasks. As if that was not enough, we perform a third level of improvisation, which is called reinforcement learning from human feedback. So, what exactly happens in that is that we have generated a set of prompts, either using a model or using human experts, and we get their outputs also. And then we have human experts give feedback on how good is the output, which is essentially like you clicking a thumbs up or a thumbs down on some model's output. Based on how many likes or how many thumbs up the output gets, a model is trained, which is called a reward model. The higher is the reward for a set of outputs, the model's policy is updated in such a way that it has a higher chance of generating similar kind of outputs in future. That's exactly what RLHF is. It is not direct reinforcement learning. It is a flavor of reinforcement learning, which is a little lightweight. But our DeepSeek and other reasoning models are going with heavyweight direct reinforcement learning, as we'll see in a bit. So what are some inference time strategies that these models use? By inference time, I mean while you are using the model, while you are prompting it. So we can do a lot of things in order to make these models perform better at reasoning tasks while you are prompting them. It has nothing to do with what has happened behind the scenes during pre-training or SFT. So what can we do? We can use chain of thought prompting, which means we ask the model to explicitly generate a reasoning trail. Break down the problem into sub-steps and then generate a reasoning trail for each of the steps. This chain of thought prompting is a bit different from traditional COT prompting type that we have studied. This is called long COT. So in long COT, your model generates extremely long trials, like thousands of tokens, and these tokens help it to spend more compute time on that problem, calculate more interconnections between the data points, and then come up with reasoning. So this is long chain of thought, not the conventional chain of thought prompting. The other strategy that we use for improving performance of a reasoning model during inference time is called decoding. So decoding means when your transformer model has already applied the attention to its inputs, and then it passes those attention scores through a feed-forward neural network. The feed-forward neural network generates a probability distribution of what should be the likely next word. It's exactly where decoding comes into picture. So instead of generating a single output, we generate a set of outputs based on the probability values that your FFN has come up with. And out of these values that have been generated for the next word or for the completion of the input, we decide which one to go ahead with based on a set of policies. This is conventional COT, like you are giving prompts to your model. This is a standard prompt. I have this, I have this, I have this, and the answer is this. Now I have this problem, you give me the answer. This is one short prompting example. You have the question, you have given the answer also, and then you are asking the model to give you answer for this question. It generates a wrong answer. And then you change your prompt to include chain of thought. So you're giving it the same question. You're also giving it the steps. You yourself have broken down the problem into reasoning steps and given it the answer also. By including this demonstration in your prompt, you are in a way nudging this LLM to also reason for this question in the similar manner. And incidentally, it has been proved that it works well. It helps the model to come at the correct answer. So long court, as I said, is not same as this court. This is simple court. I'm talking about long court here. It is different. How is it different? It essentially may not be human readable. The trace of reasoning that your model generates may not be visible to you, or it may not be readable for you. And this long court also has the chance for the model to go back and refine its outputs iteratively, which does not happen in simple court. So here's the output I got from DeepSeek for the same problem. So for the same puzzle involving the farmer, the wolf, the goat, and a cabbage. It thought for 275 seconds, which is approximately 5 minutes, and it broke down the problem. It listed all possible scenarios. It listed all possible constraints that the wolf and goat cannot be left alone. Goat and cabbage cannot be left alone. All scenarios. Like it thought for 5 minutes. And finally, it arrived at the correct answer, right? The farmer and goat should go first. Then the farmer should come back. Then farmer should take the wolf and bring back the goat. And then it should take the, cabbage and then leave it there and then take the goat also. So it came up with the right answer by spending a lot more time and by breaking this problem down into all kinds of scenarios that perhaps a human would think about. So this is another example of long chain of thought prompting where we have given this problem from chemistry, molecular chemistry to the OpenAI's model. It thinks for 4 seconds, and in this case, it has not shown you the trail of its thinking, right? It's hidden. If you want to see it, you can click here and it'll show you. But then it comes up with the final reasoning and it shows you the final answer. Long COT is seen to help models, work better at reasoning problems. Then there is parallel decoding. As I told you, decoding is the last step in a transformer where it actually generates the probability distribution and the next word to be used to complete the sequence. During that decoding step, we can ask the model to generate a lot of possible words, and then we can use a weighted majority to select which word to use. In this case, in the case of an LLM, it translates to generating lots of outputs, parallel outputs, and then choosing the output which is scored best or which is liked best by the user. During decoding, the models can also use self-refining, which means they can use a feedback either from the user or some built-in feedback mechanism, in an intrinsic or extrinsic feedback, to refine their outputs before they show you the final output, which means before you see an answer from a model, the model would have generated many intermediate answers, considered them, worked with the feedback it got from internal reward model, refined that answer, and then given you the final answer. You might have noticed sometimes ChatGPT will give you two parallel answers and it will ask you to figure out which one do you prefer. Do you prefer this response or do you prefer this response? It's somewhat like that. Then there is meta reasoning. Meta reasoning is like generating many answers and then trying to figure out which of these answers are most consistent, which of these answers have a lot of overlap with each other, and choosing those answers. Again, this meta recognition or meta reasoning allows the model answers to be more aligned to human preferences, and they have proven to be, to make models better at reasoning tasks. In addition to RL and all that, in-context learning or giving demonstrations during the prompt also help to increase the reasoning capabilities of the models. In addition to these three techniques, there is neurosymbolic AI, which essentially means you combine a deep neural network and logic-based rules or symbolic AI. While a deep neural network acts as the base model for generating text, the symbolic AI helps you to apply rules to that text and have a structured reasoning based output. Now, all reasoning essentially is planning. When you are reasoning something for your tasks, you're also creating a plan in your mind. So essentially, reasoning boils down to good planning. There are different ways, different algorithms for planning in AI. Algorithms like depth first search or A star search are planning algorithms. They tell you what is the best way to go from, one node in the graph to other node in the graph, or one cell in a grid to other cell in a grid. So these are conventional planning algorithms. They work really well, but there's a drawback. They require you to tell the entire structure of the graph. They require you to tell the model of the problem, entire environment, which may not be possible in the non-deterministic worlds in which we work, in which the real LLMs work. So besides the structured or classic planning, we use new methods. This classic planning, as I told you, uses algorithms like Monte Carlo search, A star search, DFS, BFS, and so on. This classic planning is insufficient for our LLM case where the model may not be known. You don't The LLMs cannot predict what kind of question user is going to pose, what kind of problem domain the user is going to present. So this classical AI planning has to be supplemented with reinforcement learning, which essentially means your model learns based on the feedback it receives, either from the user or from the environment or some kind of reward model. That's where the role of reinforcement learning comes into picture. It helps an LLM to plan out its steps. It helps an LLM to decide what sequence of actions it's going to take, either to solve a problem or to solve a mathematical puzzle, a logical puzzle, a mathematical problem, or to arrive at a decision based on complex scenarios or problems. So, reinforcement learning essentially helps an LLM to plan its sequence of actions. Suppose it's a theorem proving LLM, then it will tell the LLM which lemmas it should apply, in what order it should apply those lemmas in order to prove that theorem, arrive at a decision. Classic reinforcement learning involves an AI agent. This AI agent has to navigate or work in an environment. The environment, the agent acts upon the environment, and environment gives it a feedback or a state signal. Based on what feedback it receives from the environment, agent updates its policy, which means it changes its sequence of actions or how it acts. Using essentially this framework of learning from feedback, we are going to teach LLMs how to reason and how to arrive at a solution which involves complex application of complex logic or sequence of steps which involve logical thinking. So we are using reinforcement learning for LLMs at multiple levels in different forms. The very simple form is RLHF, which, as I told you, is a human labeler telling the model that I like your output or I don't like your output. Based on the human labeler's response, the model updates its policy and it generates a different kind of output next time, or it generates a different style of output next time. This is simple. However, it cannot teach the model to solve a mathematical problem or a reasoning complex puzzle. What has proved to teach the model to solve a puzzle or a complicated problem is direct RL. RL based on the verifiable outputs. That is what we call as RLVR, reinforcement learning from verifiable rewards. So this is the scenario of RLHF, where you have a set of prompts, you have a set of human labelers who give the who give the thumbs up or thumbs down, a kind of rating whether the output is good or not. And that rating acts as a reward or as a input to the model, and model is updated to comply with whatever human preference is, whatever humans like. But then this is direct RL. In direct RL, what do? We take a question, we ask a question to the model. Model generates a set of reasoning steps and a final answer. We evaluate that answer against the ground truth. Ground truth is the right answer for the maths problem or the right answer for the puzzle. And then we try to reward, we try to give the model a feedback, whether your answer was correct, whether your intermediate reasoning was correct or not. And based on that feedback, the model updates its policy. This RL, direct RL, can be applied to the overall reasoning or it can be applied to intermediate steps of reasoning as well. It depends on how fine grain you can afford to go. If you have enough compute resources, you can really afford to go really fine grain and check every step of reasoning and so on. This is the exact algorithm of how reinforcement learning on verifiable rewards helps the models to do better at reasoning tasks. We have our models here. It's a trained model, a pre-trained model like GPT-4, and we want this model to be able to work well on reasoning tasks also. So what do? We have a policy model. The policy model tells this trained model, this GPT, how to solve a reasoning problem, how to work on a reasoning problem. In the beginning, this policy model is, let's say it's random. And based on this random policy model, your outputs are generated. A batch of outputs is generated. And for each one of these outputs, the reward model gives a feedback whether this output is good or bad. How good is this? How bad is this? And then based on this reward model, your policy model is updated. Policy model is updated means the next sequence of actions may be different from the current sequence of actions. And with this change in the policy, your trained model gets a little bit better. It gets fine-tuned for efficient resolution of reasoning methods. Here's the resolution. Here you can see what RLVR actually means. Your model is already pre-trained, and then you are giving a set of prompts to your model. Based on the policy it already has, it generates a set of completions or outputs. Each one of these completions is evaluated by the reward model, which essentially means that it checks the answer model has generated and the answer that is there in the ground truth. If your answer is correct, you get a reward. The model gets a reward. If your answer is wrong, you get a zero reward. And your model is trying to your model is trying to maximize its cumulative reward. In this sequence of trying to maximize its reward, finally, your model learns the best policy and optimized policy. The optimized policy is one which maximizes the verifiable reward, which means your model is generating the answers as are present in the ground truth dataset. Here's a latest survey of all the different techniques that have been used to build reasoning models or to improve the reasoning models. They are categorized into three major categories. First is that you can use fine-tuning, supervised fine-tuning. Then you can use reinforcement learning, RLHF or direct RL, and then you can use test time scaling, which also has been shown to improve the model's performance on reasoning tasks. Test time scaling is decoding essentially, as we saw, generate a lot of parallel outputs and then apply a majority vote or decide which one of these is most self-consistent, use that output, or use reinforcement learning using a reward model and choose the outputs which is maximizing the reward. And then you fine tune on your own data set if you have resources for that. That also has been shown to improve the performance of reasoning models. Here's a summary of what are the techniques for improving the reasoning. First one is long COT. Second one is using RLHF, then using symbolic AI. You can also improve reasoning if you train on a lot of math problems and code. You can use direct RL, and of course, we can use knowledge distillation to make good small models from the big, big models which have been trained on a lot of data. So what are the future directions in reasoning LLMs? The future directions, a big area to explore is use of neurosymbolic AI. Then we can have memory augmented LLMs, which can store the previous steps, and that helps them to arrive at better reasoning pathways and better answers quickly. Then we can have multi-agent systems, which can solve different parts of the problem, which can parallelize a reasoning problem and solve it better. We can also try retrieval augmented generation to make the answers better, faster, all that. And then we can use more self-reflection and enable these models to arrive at more consistent results, more consistent reasoning substeps, and solve a problem quicker, faster, and more accurately. All right, that was about general reinforcement learning and how it helps models get better. We're talking about DeepSeek now. DeepSeek is a set of models from a company called DeepSeek. It's a Chinese company, and they are open sourcing all their models primarily to win the geopolitical war with US. So DeepSeek V3 is the foundational model. It's a general purpose model like GPT-4. The total size of DeepSeek V3 is 671 billion parameters, and this is a language generator. It can generate text very well, but it's not very good for reasoning model. So how did DeepSeek make it a reasoning model? The first step was to use some reinforcement learning on DeepSeek V3. That reinforcement learning made it into DeepSeek R10. Now, DeepSeek R10 is very good at reasoning tasks, but it does not do very good at language generation. It generates answers which are mathematically correct, logically correct, but it often uses mixture of languages, English and Chinese, or English which is wrong, like that. So it's not, it has, it is suffering a little bit from catastrophic forgetting, which means it lost some of its language skills while it learned the reasoning skills. In order to improve that, they did a bit more of training. So what did they exactly do? They applied some supervised fine tuning with cold start data. What does that mean? It means that large number of prompts and their outputs, the reasoning kind of prompts and their reasoning chains were collected, curated, and then the model was trained on that. That's called supervised fine tuning on cold start data. This cold start data essentially contained around 800,000 prompts and their outputs. Once this SFT was done, they also tried to use some SFT on general data, like not the reasoning problems, but all general problems, a diverse data set. The result of this further training was that we got DeepSeek R1. So while DeepSeek R10 is very good at reasoning, it's not that good at language generation, whereas DeepSeek R1 is absolutely marvelous at both reasoning as well as language generation. After these two models, DeepSeek also released six distilled models. Distilled models means they used two other foundational models, Llama 3 and Qwen 2.5, and they distilled the knowledge from DeepSeek R1 into these two models. These are smaller models and they are as good as at reasoning as original DeepSeek R1, which is the 371 byte model, 371 billion parameter model. So the distilled versions we have are DeepSeek R1 Distill Qwen 1.5 byte, then 3 bytes, then 7 byte, sorry, this is billion parameters, 1.5 billion parameters, 3 billion parameters, 7 billion parameters, 15 billion parameters, and 32 billion parameters. And the other version which we have by distilling DeepSeek R1 into Llama is DeepSeek R1 Llama, Distill Llama. It is in variants 8 billion and 70 billion parameters. So what else we have is that, yeah, as I told you, DeepSeek R3, R1 is based on DeepSeek V1. And what are the architectural innovations? The primary innovation is the use of a mixture of experts architecture. We'll see what that means in a bit. And yeah. So this is the architecture of DeepSeek R1. Essentially, it's a transformer model, which means it is built up of attention mechanism and feed-forward neural networks as building blocks. Instead of layer norm that we see in normal transformer, it uses an RMS norm, root mean square normalization layer, before applying attention to the inputs. After the attention is applied, you pass that output through another RMS norm layer and finally through a feed-forward neural network. Now, in normal transformers, you have multiple feed-forward neural networks, one for each token. In case of DeepSeek R1, there's an innovation that instead of a single neural network per token, we have a group of neural networks per token. This group of neural networks is called a group of experts. Essentially, an expert means a trained neural network. Now, when we are going to figure out the word to be used for completing the sentence, we use one of these or a group of these neural networks, which is exactly what we mean by a group of experts or a mixture of experts. At any stage, the experts that you have selected or routed add towards the size of the model, how many parameters you are going to fine tune or train on. This is one innovation. Instead of using one feed-forward neural network per token, it uses a mixture, a group of neural networks per token. That's called the mixture of experts model. Another innovation which is very important and which has led to reduction in the size and memory footprint of this model is that instead of using plain attention, they are using a multi-headed latent attention, right? I'm sure some of you are aware that we use multi-headed attention in normal transformers also in GPT-4 also. But in case of DeepSeek, this is a different variant of attention, which is called MLA, multi-headed latent attention, which means we are here generating latent representations of the tokens that are fed into the embeddings that are fed into the transformer layer. Instead of generating final results, we are using the latent or hidden representations itself for calculating their decoding final values, or the latent representations are passed on to the feed-forward neural network for further processing. What's the advantage of this? The advantage is that they are much smaller in size, they occupy lesser RAM, and they can also be passed on to other models. When we are doing distillation, we are actually distilling out these latent representations into the smaller models. So here is what is a normal model where there's a neural network, an expert per token, and here is what an MOE is, a mixture of expert is. You have multiple neural networks, and out of that, whichever one is producing the best output is through which the token is routed. This is also sometimes called a gate or a gated neural network. So here's a comparison of how DeepSeek has performed when you compare it with other big enterprise reasoning models like OpenAI's O1 or O1 Mini and all that. So we see that it performs pretty well, at par with these enterprise models. Again, this is language-wise and the data-wise, task-wise performance on multiple benchmark data sets. You can see it is performing really well at par with all other models, right? Sonnet or GPT-4 and itself, then O1, O1 Mini, O1 12, 17, and so on. So let's get a little bit in depth on training, what actually happened while it was being trained. So, reinforcement learning, as I said, is learning from rewards. What do you reward is exactly what gets better. What you incentivize is what gets better. So we have three kinds of rewards here. We'll see in a bit. This reward is actually searched, or it is automatically inferred based on the environment. The algorithm which we use to train this DeepSeek is called GRPO. Some of you might have heard about PPO for policy optimization. This is a bit different than PPO, much more efficient than PPO. So what exactly does a GPRO do? It uses a batch of outputs generated by the model to assign a reward to, and out of that batch of outputs it finds an average reward and uses that average reward as a baseline for that batch. What is the benefit of this? The benefit is exactly the benefit we get by aggregation. Instead of using every single value, we're using an average value. It has been observed that using GPRO, the memory footprint of DeepSeek has come down by around 20%. Another thing is that this GPRO takes care divergence as a measure of loss function between the current policy and the policy generated from SFT, supervised fine tuning, which acts as a baseline, which acts as a reference or ground truth to calculate the errors and generate the rewards. So here's the difference between conventional or standard PPO that we were using earlier and GRPO, which is introduced by the DeepSeek model. In your PPO, we were, updating the policy of an LLM based on the outputs it generated using a value model. This value model is essentially a very big deep neural network, a DQN essentially. And for every action the model takes and every reward that it fetches, it updates the model parameters. This value model is very big in size and increases the size required by a model which is using PPO a lot. The DeepSeek authors just dropped it. They removed this value model. And what did they do instead? They directly used the comparison with ground truth as the reward function. If your answer is matching the ground truth, you get a reward of plus 10. If your answer is not matching the ground truth, you get a reward of 0. Right? In case of maths problems, if you're working on creative writing or something, you can't get full rewards, right? You can't get 10 on 10. So you can also get fractional rewards if you're working on creative problems, like generating an image or writing a poem or things like that. So we start with a model, policy model. Policy model means how the output is generated, what steps are taken to generate an output by the model. A lot of outputs are generated by the model. Every one of the output is rewarded by the reward model. This reward model also takes into account the ground truth, which is generated by supervised fine tuning based on how far or how distant outputs are from the reference outputs. It assigns a reward to every output. Out of these rewards, the group computation algorithm calculates an advantage, an average score. This average score is used to update the policy, right? In case of this value function or this update model, you have a lengthy calculation of updates to each policy step. But in this case, it has become very simple and it doesn't require you to store that value model also. So here's a simple step, as I told you. You do not have a value model, and every value, every reward that you generate depends on your exact comparison with the reference true or the verifiable outputs. As an example of how you will compare the model outputs with your ground truth, here's a prompt. It goes to the reasoning model. The model generates output like this, and here is the model's final answer. It is 72. And I have a ground truth, which is either coming from pre-stored data or it is coming from a fine-tuned model, supervised fine-tuned model. There's a simple string matching. This is what your reward model does. If this answer and this answer is matching, give the full reward to this answer. If this answer is not matching, give it a 0. When you give a 0 to this model, the model is discouraged from following this reasoning trail and generating this kind of output. You can also use this verifiable rewards in case of other kind non-mathematical problems where string matching may not work. So this is we saw it in our earlier slide also. You have training data which is used to create your foundational models. Then you provide it a prompt. Based on the policy, it will generate completions or outputs. Then your reward model will compare those outputs with the ground truth, generate a reward based on how much reward you have accumulated. The model will have to update its policy. And this policy updation keeps on happening till you reach a convergence or your outputs are extremely, like, they are very good, they are correct. This is the policy update rule. Sometimes we also call it as the Bellman equation. It comes from classical RL, right? So we spoke about RLHF. So what did they observe while they were training DeepSeek R10? They observed that model developed some emergent capabilities. That is, your model automatically, like it naturally learned to generate long COT. It learned to spend more time on a problem if it's a tough problem. It learned to explore other reasoning chains, other thought patterns in order to arrive at a correct answer. Like it was not explicitly coded to try different chains of thought, but it learned to do that, right? That's essentially what we call evolution, right? Learning from the circumstances and changing the way you do things to test and see that whether you can get better results. So model learned to evolve. It learned to explore different possible options and arrive at the best answer. It learned to use more compute time. So that's the aha moment. It learned to produce a correct solution by exploring different pathways, spending more compute time, evaluating its own outputs, and backtracking to a previous reasoning step and starting all over again. That was DeepSeek R10, which was a foundational model plus RL on verifiable rewards. Now we are going from DeepSeek R10 to DeepSeek R1, which is a model which does equally good at reasoning as well as natural language generation. So what did they do to improve on DeepSeek R10? They added another reward. That reward was language consistency reward. So while they were updating the policy using reinforcement learning for DeepSeek R1, they tried to optimize for language consistency also. They will give it more marks if it is solving the problem correctly as well as it is generating the answers in good language, in correct English or in correct Chinese, whichever language you wanted to speak to you. Then, what is the training pipeline of DeepSeek R1? The training pipeline includes 4 stages. There is 2 stages of supervised fine-tuning and 2 stages of reinforcement learning. Stage 1 is cold start, applying a cold start labeled data set to perform supervised fine-tuning. Now, this data set contains lots of prompts and their responses, including the long chain of thought responses. Once this supervised fine-tuning was carried out, your model could do reasoning. The second stage was to make it work on direct RL. That's direct RL means we created a language model. We asked the model to generate answers for it. It compared the answers generated by the model against the ground truth. Whenever it wrote correctly, its language consistency reward was high. It was low otherwise. After this second level or second stage of reinforcement learning based training, the third stage of training again was supervised fine tuning, which means there were lots of prompts and their responses. How is this different from stage one? In this stage, the prompts were not specific to reasoning problems. There was a diverse set of prompts, 600 reasoning prompts and 200 non-reasoning prompts, total 800,000 examples of prompts along with their responses were used to fine tune or perform supervised fine tuning on the model in stage 3. Stage 4 again was reinforcement learning, but this was human feedback based reinforcement learning. Whatever responses the model generated, a human labeler used to give the feedback. For a positive feedback, its policy was enforced. For a negative feedback, there was a bit of update in the policy. This is how DeepSeek R1 was trained using 2 stages of SFT and 2 stages of pure RL. What are the architectural innovations in DeepSeek's architecture? There are primarily 5 innovations. The first one is use of latent attention instead of plain multi-headed attention. The second one is the use of mixture of experts architecture. These mixture of experts architecture are fine-grained, which means you have to select a very small group of experts at any time, and the model size depends only on the selected experts, not on overall structure of the network. And the third very important innovation that DeepSeek introduced was use of multi-token prediction. GPT-4 predicts one next token at any stage of its prediction, but DeepSeek predicts multiple tokens in parallel. This allows it to take a larger context window into consideration and work parallelly to solve a problem which involves it generating lots of text. The fifth innovation was that since you have a lot of experts, a mixture of experts, how do you balance load between them? How do you load shed one? If one expert is, having to work a lot, how would you transfer the load to other one? This load balancing algorithm also was an innovative one, which means it brought down its memory footprint, its compute time, and it also optimized the performance. The final innovation that DeepSeek did was use of a quantized version of its weights. Entire training was carried out using floating point 8-bit values. The weights that they trained with were 8-bit floats for the entire duration of the training. Now, some of you might have the question that this might have led to the loss of precision and so on, because normally the weights are FP16 or FP32. But then they have used these weights and they have used the innovative quantization training algorithms also. So the overall performance of the model has not been compromised much. During pre-training, they used, as I told you, floating point 8, and the cost of training was just 2.6 million H800 GPU hours, and after pre-training, it was just zero point 0.1 million GPU hours. And this was the innovation in pre-training. What was done in post-training after the model was trained? They distilled its knowledge into smaller models. And of course, those smaller models are equally good at reasoning tasks. Knowledge distillation is transfer of learned parameters, learned concepts, latent representations from a bigger model which has been trained longer on a lot of data into a smaller model to make the smaller model almost as good as the bigger model. Uh, so there are 6 distilled models, which are as good as the DeepSeek R1 model. So there's a question, is distillation better or is reinforcement learning better? It has been shown that distillation has been shown to perform better. If you're creating a distilled model, it is better as compared to only applying reinforcement learning. But then if you perform reinforcement learning on top of distilled models, it will be even better. What are the real world applications? When should you use reasoning models? Now reasoning models is not something we require for simple task of, help me write an essay or help me complete this question paper or help me write this paragraph or summarize this article. We don't need reasoning models for those kinds of tasks. Plain language models are just fine for them. When do we need reasoning models? We need them when we are doing scientific research or when we are solving mathematical problems. We are proving some theorems in either physics, chemistry, math, or other such domains. When you are trying to work on automated decision making, when you are debugging a large amount of code, or when you are making interactive systems which involve logical reasoning, critical thinking, and so on. What are the emerging trends? Emerging trends, of course, are the use of reinforcement learning, use of long caught, then use the self-evolving or emergent capabilities, exploit the emerging capabilities of reinforcement learning. Then we want to go in for less and less of RLHF. We want to reduce the human supervision because, again, that may be costly and you may not always get good set of labelers. And finally, distillation is an emerging trend. Have model trained and then distill the knowledge into multiple smaller models. What are the open challenges in reasoning models? One big challenge is that when you are using long chains of thought, these long chains of thoughts may be chains of thought may be hacked. Somebody may inject some malicious intention into these chains, and they can break into your system or they can corrupt your data or something like that. Another challenge is how to balance between reasoning capabilities and general capabilities. As we saw what happened with DeepSeek R10, it got some catastrophic forgetting. When we built reasoning capabilities, it lost the capabilities of language generation. So we need to balance that. The other one is to find out what is the just right amount of supervised fine tuning. Supervised fine tuning is a costly affair. We want to keep it just at an optimum. And then we also want that your models should not keep on reasoning for long for what is not required. And then these models, how do we efficiently host them? How do we serve them to the public? Here are the references. And now we're quickly going to look at how to use the easiest way for us is to go to chat.deepseek.com and ask your questions here directly. This is your R1 model. It is capable of reasoning. You can upload your documents and you can tell it to generate a literature review for you. For example, I uploaded these two papers and I asked it to generate a literature review. It should contain the research gaps identified. It should contain what methods are described in these papers and what results are described there. For now, the length of documents that you can upload into Chat DeepSeek is 5 MB. So based on these two input papers, it has thought for 21 seconds, and then it's giving me entire thought process, what it thought and what it figured out. And it's finally combining and giving you an output which contains the research gaps identified in both papers, the methods described in both papers, and the research results discussed in both papers. Now, my intention here is not to automate the process of research for you, which is totally unethical. The point is that they can help you do your stuff quicker and efficiently. Absolutely necessary is that you yourself read and verify whatever the model is generating for you. Even though it is a reasoning model, it still is a model, right? It's not an expert. Other way to use your DeepSeek locally is to use Olama library. Olama is a library and a framework which allows you to download and run models locally on your machine. It can provide you big models. If your machine allows it, go for a big model. It can also allow you to work with smaller distilled versions of a model depending on what compute resource you have. So how do we use Olama? You have to go to olama.com, go to downloads, download an appropriate version for your computer. Once you have downloaded its exe, double click on it, the normal installation will happen. It will take, let's say, 1 minute or 2 minutes, depending on the compute you have. Once this installation is over, you can verify that it's there on your system in the start menu. Then on the command prompt, open a new command prompt and type Olama commands. It's a command line interface based framework. So you can type commands on the command prompt. Olama pull command helps you to download a model. Here I am downloading the Mistral model. Once your model is downloaded, you can run a model. You can do Olama run name of the model, or you can also pass a specific prompt, Olama run Mistral and the prompt. You will see your output in the command prompt itself. That means this model is downloaded and it is available in your local machine. Of course, for running Olama, you may have to install a certain set of dependencies, especially if you are using Olama in Python, in Jupyter Notebook, or in your any other Python editor. So if you want to see the features of the model, the command is Olama show. Then if you want to delete a model, Olama RM. If you want to create your own model, then you need to have a model file. With that model file, Olama create function, Olama create command helps you to create a new model. Once you have created a model, you can serve that model to outside world. Like you can host that model with Olama serve. If you want to see which models are currently running, the command is Olama PS. When you want to stop a model, of course, the command is Olama stop and the model name. This is how you will verify whether Olama has correctly installed or not on your computer. So I want to run DeepSeek, right, on my machine. For that, on the command prompt, I will type Olama run DeepSeek R1. And since my computer is restricted, I don't have a lot of RAM and all that. So I will be using 1.5 billion parameter version of DeepSeek R1. DeepSeek R1 colon 1.5B will get me the model, distilled model, which is 1.5B. And after this, you will get a prompt and you can start prompting this model right from the command prompt of your local machine. This entire model comes to your computer, sits there, and you can work it locally. If you want to use Olama programmatically in a Jupyter Notebook or in an IDE, you need to pip install Olama library. Olama is a Python library which helps you to use the Olama that you have installed in Python. So the necessary requirement is that first you have to download and install Olama like this. And then you have to install the Olama library in pip or in your Anaconda prompt or in your Python prompt or in your Jupyter notebook. Once you have installed the Olama library in your Jupyter notebook, you can import it. Then you can start a new chat. In the chat, you have to specify which model you are chatting with, what is your message, and all that. Once you have written your message, you can submit it to the model and print the content that you want out of the model. For example, here I have on the command prompt itself, I have started Python prompt and imported Olama, generated a response variable, olama.chat. I've specified the model, DeepSeek R1 colon 1.5b. Now it is mandatory that before you run this prompt, this Python code, you should have done Olama pull or run. With Olama pull or Olama run, you would have downloaded this model. Only after download can you call it in Python program. Once we have done that, we have initialized a message. The message has a user role, like role and the prompt text. You can pass this to the model and you can print the response from the model here. Here's the response from the model. So I am going to show you a bit of code also before I ask you to give the feedback. So let's see that.
I mean, how much memory will it use when I, install? I mean, when I.
1.5 billion, which means around 5 GB you should have.
Okay.
So is this Jupyter notebook clear, visible?
Yes, ma'am.
So here is a new Jupyter notebook. Of course, you need CUDA for this and some other dependencies. We'll talk about them in a bit. So I imported Olama. Then you create a chat API. You specify which model and you specify your prompt, right? For example, I'm asking it, tell me about quantum entanglement. Here's the output. What you see between these two tags is its reasoning chain. All of this is its reasoning. It is talking to itself, right? It is breaking the problem, understanding the problem, and everything. The standard format of a reasoning LLM. Whatever is between think and slash think tags is its reasoning profile, is its reasoning trail. And based on its reasoning, here is the final answer. It is giving me the final answer. This is a simple way of chatting with Olama in the, I mean, it's a simple way. If you want to use it or you want to serve it, you can create a GUI for this. For that, I'm using LangChain here because I want to do RAG. So I will be serving this model as Gradio in Gradio. I have imported these things, and for sure you will first need to install them on your prompt using pip install or conda install, whatever you're using. Here's a function which will, I will upload a PDF file. This function will process that PDF file, which means it will split that PDF file into chunks. It will convert that PDF file into numerical embeddings. It will store those embeddings into a ChromaDB, a vector store, and it will be able to retrieve from the vector store whatever is relevant to my question. It will be able to do semantic search and retrieve the parts of context which are matching my question, right? This is a small helper function to combine all the pages of the document. Then here is my function which invokes DeepSeek and which asks it the question. This function, I have formatted the question in a proper way. Then I'm constructing the API, I'm specifying the model, I'm specifying the question. This question is whatever my formatted prompt is. We will be generating formatted prompt from users' input, which they will give in the Gradio interface, right? So it will return the final answer. Here's my rank chain function, which will get the retrieved content from the document, and it will combine that context along with my prompt and submit the final prompt, like prompt plus context, to my Olama for questioning. It's a simple ask question function, which will be invoked on the event in Gradio interface. This question takes the text from text box. It connects that text with it passes that text to that splitter, chunking and all that, and it gets me the result. Here's the Gradio interface. In this Gradio interface, here's your invoke function, ask question function. Here are a simple set of widgets on my Gradio interface, and here's what it looks like, right? It's allowing you to update a file, upload a PDF file, and you can ask a question about that file. So what do? We click on this. I think I'll have to run it all over again. So you can upload a file and ask it to give you answers, right? And ask a question. What will happen is that your prompt will be converted into an embedding. The file will be converted into an embedding. Relevant context will be fetched from the file. That context will be passed, that prompt plus context will be passed to the DeepSeek R1B, which you have on your computer, and your output will come here. The output looks exactly like what we saw on the command prompt. I'm not doing this because it's taking a bit of time, and I think I have to run the previous cells also. So this is how you use DeepSeek R1 1.5b locally on your own machine, even if you do not have access to the internet. You may require to install all these libraries, dependencies beforehand on your computer. Right. So with that, it's 5:58. I'm right on time. Are there any questions? Are there any? Do we have any questions?
Yeah, can I go ahead with the question?
Yes, sir, please.
Long COT,
Yes.
is it trial and error or is it just getting some approximate intermediate steps? Why I'm asking is if it is trial and error, then it is more like conventional backtracking kind of solution, right? Not
Yes.
algorithmic, but at least at a very high level, subjective level.
Yes.
How does it work? Like, is it trial?
Long code during training, during reinforcement learning based training, or during SFT is trial and error. So once the foundational model is trained, its next phase starts, which is SFT. During SFT, we generate the prompts, either humans generate it or other models generate the prompts, and humans or other models generate the reasoning trails also, right? So they may include a bit of hit and trial, or they may be incorrect, or they may not be completely correct. These together, the prompts and the reasoning trails, are fed back into the model. And then there's a
Yeah,
reward model.
Got it. Yeah. So in that case, suppose you gave that earlier puzzle, right? So goat, farmer,
Yes.
cabbaging.
Yes.
So similarly, we give say conventional AI problems like say it queen's problem or something like
Yes.
that, right?
Yes. Yes.
So and fine. So will it get stuck because of computational complexity, or can it really find the solution?
Yes, it depends on the model you're working with and which version of the model. Distal 1.5e does get stuck. It doesn't work on complicated problems. With small reasoning problem that we saw, it works well, but it may not work with a research problem involving a lot of computation. But DeepSeek R1, the 671 billion parameter model, does work fine. It has been demonstrated in their benchmark results that it does work well.
Sure. Thanks.
Thank you. So I would really appreciate if I can have your feedback. You can either scan this QR or just go to this URL and provide me a feedback. Thank you very much for joining me today, and it was a pleasure to share my knowledge with you. Thank you very much.